fermionic creation operator C, but we project out any nearest neighbor fermion. So we put a hole projector on both sides of the fermion. Right? So you can create a fermion only if the two nearest neighbors are empty. And likewise, we have a de-annihilation operator. So here's an example. So suppose you have this state with fermions filled like this, and you would apply this D1 operator. So D tries to create a fermion at this first spot, but because there is a fermion in spot 2, it's not allowed to do so, because it can only create where the nearest neighbors are empty, so D1 acts as 0. At the moment. So you can think of periodic boundary conditions in this case, right? So the left boundary, which would be this set, is open, but the right boundary is filled. So if I would act with D7, so that's here, that's in the middle of these two, so there I would be able to insert a fermion like that, and I would also be able to remove that fermion again with the annihilation operator. Okay, so we just have these operators that are, you can think of them as fat fermions. They don't allow nearest neighbors. With those operators, you can write down what turn out to be SUSY charges. So you can write down this operator Q as a linear sum of these annihilation operators D of fat fermions, and likewise the creation Q dagger, sum over creation operator, and you can check that Q square equals 0. And you can write down a supersymmetric Hamiltonian as the anticommutator of Q dagger Q, and if you work it all out, you'll find that it has these terms. So this is, I guess, pseudo-local in the sense that it only involves nearest neighbor D operators. So in terms of the original fermions, that would require that spans about 2 or 3 sites. So there are some diagonal terms here that count the number of fat fermions, and then there are some hopping terms over here. So this was done in early work by Fendley, Nenhuis, Houtens, and de Boer. That this H, this Hamiltonian H, is a lattice realization of what is called n equals 2 supersymmetric quantum mechanics. So there's some really nice properties, this Hamiltonian. So we can write this in a slightly different way. So remember, I had these diagonal terms, and they count the number of fermions. So I can actually take those out and rewrite this Hamiltonian in the following form: that this H has a constant, which is the length of the lattice minus 2 times the number of fermions in the sector that I'm looking at, plus a sum over hopping terms, so 2 kinetic terms here, and a quartic interaction term, which is repulsive. Okay, so what are the nice properties? Two essential properties are that the supersymmetry implies that the ground state is exactly 0 for any system size, no finite size corrections, and that non-zero eigenvalues are all positive. Okay. So just want to point out a relation to the spin chain we all know very well. So this model is actually related through a mapping to the XYZ spin chain. And this mapping goes as follows. If you have a fermion configuration like this, then that maps to a upspin in the spin chain. And if you have 2 empty sites like this, then that maps to a downspin. So you can already see that something funny is going on. There's 3 sites mapping to a upspin and 2 sites mapping to a downspin. So what happens here is that the fermion chain of length L maps to spin chains of length L minus the number of fermions in your system. So different sectors of the fermion model map to spin chains of different lengths. Right, so here's an example. You can just check for yourself that this fermionic configuration maps to, with this mapping here, maps to this configuration of spins. And this configuration of fermions, which is the same length as above, maps to a spin configuration of a smaller length than the one above here. So under that mapping, you find that this Hamiltonian is equivalent to the appropriate sector of the spin chain Hamiltonian, the XXZ spin chain, with delta equals this notorious value minus a half. And we have to always be very mindful that this fermionic chain has length L, and the spin chain has length N, where N is L minus the number of fermions of the sector that you're looking at. But anyway, in this way, the two spectra are related. Okay, so a few years ago, I was in Amsterdam and I talked to Bernard Nienhuis there, and we looked at, well, he was involved in this development. And let me go back to the supercharge. So there was this supercharge here, which was the sum over all annihilation operators of fat fermions. And Bernard had thought of maybe we should also include a manifest particle hole symmetry. So we should be able to have fat holes as well, right? So you have if you have three fermions in a row, you can remove the middle one. And so that's what we started looking at. So we included new operators E that are annihilation operators, so they remove a hole at side I, provided the nearest neighbors are filled. Right? So this is non-zero only if you have, here's an example. So E3 acting on this state, there are three fermions in a row, and so it can remove the middle one and get to this configuration. And there's a minus sign because when I remove the third one, there's an odd number of fermions to the left of it, so I get a minus sign. And so what we did was add that operator to the SUSY charge. So now we looked at a SUSY charge, Q dagger, which was the sum over the creation operators of fat fermions plus the annihilation operators of fat holes. And so that introduces a manifest particle hole symmetry. And you can again check that that the Q square equals 0, and that this is a SUSY operator, and then you can compute the Hamiltonian again as the anti-commutator of Q dagger Q. So if you do that, you find three different terms. One term only consists of the D operator, so that was the original Hamiltonian that we had before. The second term only consists of E operators, so that's basically the same Hamiltonian as the first term, but with particle hole symmetry. And then there are mixed terms. So when you compute this anti-commutator, there's cross terms where the D and E operator is mixed, and so you get this term with mixed E and D operators in it. So we started looking at this Hamiltonian. So just to show you what happens, what these operators do, here's a configuration of fermions, of the original fermions, and let's say I want to act on it with one of these mixed operators. Let's have a D dagger J. So I'm trying to create a fermion over here, and then after that, after I've created a fermion over here, I can insert a fermion over there with E dagger. So you go from this configuration of fermions to that configuration of fermions. So what this operator does, it inserts two fermions. Right? So the number of fermions is no longer conserved. So we can create a pair of fermions. What is conserved, however, is this domain wall. So there is a domain wall separating a region from with fermions to the left to an empty region to the right, and that domain wall just hops 2 places to the right. So while the number of fermions is no longer conserved, the number of domain walls is. Likewise, there is this term that when it acts on such a configuration, it will remove those 2 fermions, and so you can also remove decrease the number of fermions like this, but again, the domain wall remains and it just moves 2 steps to the right. Then there were these terms, so this describes the sort of the dynamics of these mixed terms. To look at what these original terms do, they were describing hopping of individual fermions. So what do they do with domain walls? Well, if you have an individual fermion, it means there are 2 domain walls very close to each other. And so this term describes an interaction between domain walls, where one domain wall hops over the other one to go to this configuration. So the way we think about this, what this does on the fermion, it hops the fermion 1 place to the right. What it does to domain walls is, the way to think about it is that this domain wall hops over the other domain wall. And you get to that configuration. And then you can do something similar with domain walls that separate a single hole. Okay, so we have that. In summary, we have domain walls of this type. We call them 1, 0. So they are domain walls between a filled region to the left and an empty region to the right, and they can move 2 steps to the right or 2 steps to the left. We have 0, 1 domain walls where the empty region is to the left and the filled region to the right. They hop either to the right or left, but they have a minus sign because of the fermionic nature. And then there are these interaction terms. Okay, so that's all nice. And so we studied this model, and now I will show some properties later on. But over the years, we discussed this with Carl Jan, and he noted that there is this Fendley-Schoutens model, we call it, which is a very different type of supersymmetric model. And I want to say a few words about that. But it had very similar properties. So that becomes important later on. So I want to say something. Maybe first I want to show you a picture. So what they did is consider 2 XX chains. So you have an XX chain at the top and 1 XX chain at the bottom, where spins can hop from along the chain, and so with some rate. But if they hop from one side to the next, and there is a fermion in the bottom chain, they get a phase factor of -I or +I, depending in which way they hop. So there are 2 XX chains, but there is an interaction between them in the sense that the hopping rate depends on whether or not there is a spin in the bottom chain. And vice versa, they can hop along the bottom chain, but then there is a phase factor. So for example here, this spin can move over there with a phase factor -I because there is a spin in the top chain. Okay, so that picture is maybe more informative than these formulas, but I want to show them anyway so that you know that there are concrete formulas underlying them. There is this SUSY charge, Q. It's a bit complicated. So it's a product of annihilation operators on the one chain and creation operators on the other chain. And here as well. So there's the odd sides label the bottom chain and the even sides label the top chain. And then there are these phase factors. So there are certain phase factors, e to the alpha here and there. And these alphas are sort of non-local phases. They depend on the number of spins to the left of the site that you're looking at. As it turns out, I mean, this is again a SUSY charge. You can check that Q squared equals 0, and you can compute the Hamiltonian through this anti-commutator, and it looks like this. So there are these hopping terms here along a side. So if you're at the top side, you hop from j minus 1 to j plus 1. And if there is a fermion at side j in the bottom chain, then you get this phase vector I. There are terms like that. And aside from these hopping terms, then there are some chemical potential terms. Okay, so this was a model they studied. It corresponds to this. And actually, this model on a system with open boundaries, so here you look at open boundaries where you fix the first side to be empty. It turns out this model is integrable. So, of course, the XX chains are integrable by themselves, but even with this sort of marginal coupling, they remain integrable, and you can write down the energies, and it turns out to be free fermionic spectrum. Although the degeneracies of the spectrum are not the usual ones. So the energy eigenvalues are just free fermionic, right? So it's cosine of momenta, where the momenta are multiple roots of pi over L plus 1. Okay, so they had some reasons to look at this. So I've shown you two models now, two very different models. So there was this Ventlies-Schoutens model, which was a model of spins or fermion. You can transfer them into fermionic language and have this supercharge on a zigzag ladder of chains. And then was the domain wall model, which had this supercharge, the domain wall model or the fermionic model with manifest particle hole symmetry. And so when we studied these the properties, it turned out that more and more these the properties were very similar between the two models. And I think it was at this meeting in Beijing where Carl-Jan started to maybe believe that the models could be the same. It could be a mapping between the two, and that turns out to be correct. So there is actually a mapping between these two charges. You can write it like this. This Q is TQ Fs T dagger, where T is a product of three operators. So to get this mapping, what we have to do is first move to a different basis, if you like. So there are these operators M and gamma. I will show them on the next slide. That M turns creation and annihilation of domain walls into hopping of domain walls, and the second operator gamma turns domain walls into particles. And then after that, we have to adjust the phases. To get these phases here, we have to sort of insert them through this T operator. So M and gamma are relatively straightforward, just a change of notation, if you like, while P is more complicated, and it has to adjust these phases. Yeah. Sorry? Yeah. Well, we can do it for both. So I'm a bit fuzzy on that. But you can do this for both open and periodic, but I didn't want to do it. Yeah. I will say something about that later on, the difference between open and periodic. But anyway, you can regard this transformation as some sort of generalized Jordan-Wigner transform, except where these phase factors that are encoded in P are quite non-trivial to figure out. So this was work by George and Sasha to figure out exactly these phase factors. Anyway, so we've got these two models with very different physical pictures and very interesting properties. So let me, want to say something about the properties before doing that. So here's some explicit form of these operators. So M is a product of differences of fermionic operators, so it has a very explicit form. It actually has a nice property that it inverts the spectrum. And there's a second operator, gamma, that turns domain walls into particles, and you can write that explicitly as a product as well. And then this operator P has a sort of explicit form, but that's too complicated to put it on this slide here. All right. So going back now to the domain wall picture, so the results I'm going to present hold now for both models, but I want to present them in terms of the domain wall picture. So just to remind you, we had operators that in the Hamiltonian that would hop domain walls by two sides, to the right or to the left. And the two types of domain walls, these 1, 0 ones and the 0, 1. And the 0, 1 domain walls hop with a minus sign because of the fermionic nature. And then there were interaction terms between domain walls, where two domain walls could jump over each other. So we started looking at the spectrum, or at least Bernard did, and Fendley and Karajan did it as well earlier on. And if you just compute the spectrum, this is the picture you see. And so you see that there are many energy levels that have quite high degeneracy, right? So they're almost all, well, in fact, all energy levels have some plateau. So there is some degeneracy that is quite large. So here's a table. So one column has all the energy eigenvalues, and then there is the degeneracy. And you can see that the degeneracy is always a power of 2 in this example. So there's quite high, sort of extensive degeneracy of every energy level. And they are powers of 2. So one question was, how can you explain this large degeneracy? So we started looking at symmetries. Well, there is the supersymmetry, of course, that computes with the Hamiltonian. We have explicitly a particle-hole symmetry by construction, and that is implemented by this product of Majorana fermion. So you can show that this computes with the Hamiltonian. There's also a domain wall, non-domain wall symmetry, and that's a different operator. That's this operator here. And then there is a shift symmetry. And so this shift symmetry allows you to move between sectors where you have, say, what it does, it shifts the domain wall by one step. So if you have a number of domain walls at even sides, then this creates a linear combination of states with at least one domain wall on an odd side. And then this M operator that reflects the symmetry. So there are a number of symmetry operators, but these are all discrete symmetries, and they don't explain this very large, they explain some bit of the degeneracy, but not the very large one. So this is not enough to explain the extensive degeneracy. So we wanted to explain that. Then we started looking at whether this model was integrable. Remember, the original model was integrable. It was related to the XXZ spin chain, so we could check whether this one is also integrable, and it is. So you can do a beta ansatz, and in fact you have to do a nested beta ansatz here. So to do that, we have to actually implement a nested coordinate beta ansatz because we don't have an R matrix. We can't do algebraic beta ansatz just yet. And we noted that there is conservation of all domain walls, but there's also conservation of odd and even domain walls. If you remember, the domain walls hop with two sides, either to the right or the left. So if they're on an even side, they remain on an even side. And so the dynamics of the model preserves both odd and even domain walls separately. And so the total number of domain walls is a good quantum number, but the number of odd domain walls is an additional quantum number. So the two quantum numbers, and therefore you have to do nested beta ansatz. And coordinate nested beta ansatz looks like this. So we have a wave function that depends on the coordinates of all the domain walls. There are m. And then P1 to Pk are the indices of the odd domain walls. So there are k odd domain walls, and the coordinate of an odd domain was xp sub I. And so we want to know these coefficients psi. And you can go through the motions. It's a somewhat laborious calculation, but it can be done. And you can show that this is indeed satisfies the eigenvalue equation. The beta ansatz works, and the spectrum is described in this way, the usual way, where the z's are the beta roots, and they satisfy the following equation. So, and now I'm talking about periodic boundary conditions. So with periodic boundary conditions, the z's satisfy equations of this form. And you can see that there appears a second set of beta roots. We call them U, and they are associated to the nested level of the beta ansatz. So there are two families of beta equations. One is for the zj's, so with a product over all the u's. So each zj has to satisfy this equation, and then every uk has to satisfy this equation where the product is now taken over all the z's. Yeah, it's okay. Yeah. Yeah, there's something similar in the Hubbard model. No. No. So it's not a limit of the standard Hubbard model. So I'm envisaging that you can maybe add another parameter like a field or so in the Hubbard model and then take that field to infinity or something like that. I could imagine, but not of the standard Hubbard model. And for example, you can see that in this equation, in the Hubbard model, the left-hand side is non-trivial. There is no limit that makes the left-hand side trivial and the right-hand side and remains the right-hand side as a non-trivial. Okay, so now that we have the spectrum in terms of beta ansatz, we might be able to explain this large degeneracy that we found numerically. And indeed, you can check that it's possible that if you have a pair of u values and they are each other's negative, so if u2 is negative u1, then there is a solution where z to the L is equal to 1. Let's go back. So z to the L is this product over the u's. So let's take m equal to 2. So I have only two factors of this product. But if the u1 and u2 are each other's negative, then those two factors are each other's inverse. So they cancel each other. And that's what's written here. And you find that z to the L is equal to 1, and these two factors cancel each other if u2 is negative u1. And the same for the second set of beta equations. They just can be satisfied by solving this equation for u. And so if you have such a pair, you can just create that at zero energy because it doesn't contribute to the eigenvalue at all. Right? So if z is equal to 1, z to the L equal to 1, then I can introduce such a pair in the beta equations, and the beta equations don't change. I still have that z to the L is equal to 1, and I just need to solve this second beta equation for u, and I don't change the energy at all. So if you are at a given energy level, you can just create excitations with zero energy. And you can create many of them. Every time you create such a pair, you create a new eigenstate but with the same energy. So that creates a very large degeneracy. So we think of these as Cooper pairs. Yeah. Yeah, it's extensive. Yeah. I'm not sure I understand the question. Yeah. Oh, yeah. Well, I'm not the right person to ask. Maybe you can address this question about the Witten index. Yeah. Yeah. So this is one way of understanding this large degeneracy by being able to create zero energy Cooper pairs. And indeed, if you don't do the counting carefully, you can explain the full degeneracy of the model. I should say that the beta equations or the beta ansatz doesn't give you all the eigenvectors explicitly. It does give the full spectrum, but to get all the eigenvalues, you have to use these symmetries to, if you in a certain sector with a given number of domain walls, the beta equation will only give you a subset of the eigenvectors. The other eigenvectors come from different sectors, and you get them by applying the symmetry. Okay, so of course the ground state energy is zero by supersymmetry. You can look at excited states, and because the energy is given by this cosine, the energy gap is 1 over L squared. It's a simple calculation. And so the next thing we wanted to do is create a mass gap between the ground state and the excited state, so to protect the ground state. So question is, can we introduce a mass gap in this model and maintain supersymmetry? And so this was a suggestion by Carl-Jan that we should maybe look at a staggered interaction between the sites. So we introduced this inhomogeneous parameter, lambda I, where lambda is 1 minus lambda I if I is odd, and 1 plus lambda if I is even. So we have a staggered interaction along the domain wall chain. And okay, so we can plug that into the supercharge, compute the anti-commutator, and again the Hamiltonian consists of 3 terms, and these terms are here, and now there's this lambda parameter showing up. So this is the term with only the D operators. It has some lambda dependence. The term with only E operators, there's some lambda dependence, and then the mixed terms with also some lambda dependence. This indeed creates a mass gap if you vary lambda. But more so, the model remains integrable. So again, we can do a beta ansatz for this model, and now the eigenvalue is given by some lambda-dependent constant plus this kinetic term, the one particle energy. And the nested beta ansatz wave function can be written explicitly in this way. So we have the standard plane wave form, z to the x for all the coordinates. But if you have an odd domain wall, you have to introduce some sort of a generalized rapidity, some function phi that depends on u parameters. And it factorizes like this with some functions f and g. So there's a very explicit form for this. And so again, this model is integrable, and we can do both the periodic case and the open boundary case. So for the periodic case, the scattering factor now changes, and it will now have this constant c in here. So now it starts to look more like Hubbard. So this scattering factor is exactly like Hubbard, where this c is given here, so it's just lambda dependent, and v is just u rescaled. But again, the second beta equation, the right-hand side looks like Hubbard, but the left-hand side is trivial. And that you can't get by direct limit. Yep. Is that true? Yeah. So, okay. Yeah, okay, so maybe you have to do that. Yeah. Yeah, that's it. That may be. Anyway, this is a supersymmetric, like a manifestly lattice supersymmetric model with a mass gap, and it's integrable, and so it has some nice properties. But this is work in progress at the moment. I can't really report on that. There's one more interesting fact that I want to report is that if we do this for open boundary case, so for certain open boundary conditions, the Bethe equations look like this, and you can see that this dependence on the second family of beta roots has completely disappeared. So if you tune your boundary conditions in such a way, the spectrum becomes free fermionic, again, if the system size is odd, and non-interacting if the system size is even. So non-interacting means that this only depends on Zi, but not on all the other Z. So this is somewhat interesting in the fact that the beta ansatz wave function depends on these U parameters, but they're not fixed by the boundary conditions. So there's a free parameter floating around. And that means that must be a very large degeneracy in that sector, right? And that this U is somehow a generating function parameter for all the beta states in that sector. And indeed, if you look at the spectrum numerically, there's extremely high degeneracy of the even when you switch on lambda, there remains a very high degeneracy of all the levels, like exponential. Okay, so that's it. So my conclusions are that we have this SUSY lattice model with two very different physical pictures. We introduce staggering while maintaining integrability and maintaining supersymmetry, but introducing a mass gap. So we have a gap model with exponential degeneracy of all the levels. So there's a few questions to be asked now. So what is the underlying symmetry algebra, which we don't fully understand yet? So that should be interesting from a mathematical perspective. So we have this zero energy BCS pairing mechanism, and the next thing we're trying to look at is, are there any topological phases in this model? Right, thank you.